Good morning, all. Thanks for joining in today's Advanced Air Mobility webinar that is organized by IEEE Vehicular Technology Society. And today's speaker is Mihail from North Carolina State University. There is a significant and important work that is going on the platform called AERPAW, and Dr. Mihail is going to talk about the ongoing work. The webinar is about 40 minutes, and then you will have time to ask questions, and then they will be answered live. Hope everyone enjoys the meeting. Thank you. Thank you, Mihail, Dr. Sichitiu, and then go ahead and then begin the webinar. Thank you.
Thank you, Kamesh. I'll take it from here. And what I want to talk about today is about AERPAW in general, and in particular from AERPAW, right? I will explain what it is and why it is that we do what we're doing, and in particular about the AERPAW vehicles, which you will see that are front and center to what we're doing and the reason we're doing what we're doing. Okay, so I'll start by giving a bit of motivation on what this AERPAW is all about and why it came to be, and then we'll talk about our drones, our UAVs, and we're gonna start talking about the hardware, and then we're gonna go talking about the software. Okay, so at its core, the perceived problem at least, but probably also a real problem that NSF noticed was that a lot of the research that's done in universities and national laboratories fail to translate to product development and products incorporation, because there is the valley of death between the theoretical research on the left and the incorporation. So what the idea is to have programmable testbeds that can bridge this gap. So the research done in universities, if it can be implemented on a testbed, then it's going to make it so much easier for corporations to take it on. So to this end, NSF funded 4 different platforms for advanced wireless research. And the first 2 were Powder and Cosmos, that are Salt Lake City and West Harlem. Then it was us, number 3, AERPAW, right? This is us. And recently, ARA in Iowa, in Ames, Iowa, has been also funded and started their activities. They just became available a couple of weeks ago. And as you can see, each of these platforms have their own particular characteristics. All of them have wireless at their core, but in addition to wireless, some specialized on massive MIMO, others in millimeter wave research. What we specialize in AERPAW is unmanned aerial vehicles and mobility. We are the only one out of these 4 platforms to have unmanned aerial vehicle and mobility, and we offer these facilities to our experimenters, which, as you'll see, dictates a lot of what we're doing. I want to point out that although today I'm making this presentation, there are a lot of people that contribute in one way or another, either directly or administratively or project management, or just supporting our activities, laying fiber, building towers, and this is just the people that we have pictures for, and then a lot of other people that literally couldn't fit. And I want to make sure that to highlight that just the fact that you are a student over here doesn't mean you didn't contribute a lot to the project. As a matter of fact, this guy, John Kessler, I think he wrote more code to this entire project than anybody else on this page. Likewise, Mark is last here, but he single-handedly designed and built our UAVs. So it's truly a team effort. It's a lot of work went into this, and it continues to go. So I'll show you what we're doing. So if I would be to summarize what our platform is about, is we have two deployment areas. One is in Centennial Campus, which is more urban, but then we have a rural flying field that has 5 fixed nodes. So they are the 4 yellow ones and the reddish one over here. And the fixed nodes have computers at the base and radios at the top and antennas. And then paired with these fixed nodes, we have mobile nodes. And that's what today's webinar is going to focus on. In what are the mobile nodes at AERPAW and how they're built and how they're designed. And the mobile nodes can talk directly to the fixed nodes, or they can talk to each other. The fixed nodes can talk directly to fixed nodes, right? So there is a ecosystem, and this is the difficulty, is making available these portable nodes on these vehicles to our experimenters. That's our main job. Okay. By the way, if you do have questions, do not hesitate to ask. Every once in a while, I will stop and check the chat and try to answer the questions. Okay. If you would rather keep them at the end, I'm okay with that too. So we're gonna now jump into the hardware part of the talk, and I'm gonna start with what we identified as being the requirements based on what we need to do. And our wireless colleagues, of which I'm one of them, but only one of them, told us that our drones need to lift quite hefty payloads, right? Somewhere in the range of 3 to 10 kilograms, should fly at least for 30 minutes, right, to get meaningful experiments. All this while staying a small UAS according to FAA, so we can fly under Part 107. So that means the whole all-up weight needs to be under 25 kilograms. And we need to be able to interchange payloads. So we have, as shown here, and I'm gonna give you more details, it's our portable node fits on any of our drones. So same, easy to change batteries. We want to have, everybody wants to have, but especially, since we're gonna fly a lot, then we want to have reliable machines, and if possible, use an open design and with commodity hardware. And this turns out to be essential requirements that guided our solution. In terms of software, if at all possible, we would love to have an open autopilot software, and the reason for that is we have particular requirements that not all autopilots can satisfy. So then we'd like to be able to get our fingers in the autopilot software and change it if needed. We want to have open communication software, open vehicle control software, a standard ground control station. You'll see in a second, we need a software in the loop solution for our drones. And ideally, right, this is not a hard requirement to have different programming languages and different levels of experimental access, but these were desired requirements, not necessarily hard requirements. So that's what we came up to do. What I didn't make clear is what I'm doing in this project is primarily the design and implementation of all vehicles. So that means drones and rovers, as well as the portable nodes. So everything that flies or moves, as well as the emulation environment. And we'll talk a little bit about that as well later, right? So these are my primary responsibilities in this project. Now, if I would have to summarize kind of everything I said, is that AERPAW is all about having programmable radios on programmable vehicles. And today, I'm going to focus on the programmable vehicles part, and I'm going to explain how that is achieved in AERPAW. Okay. So the first thing I want to point out in terms of hardware, the way we solve the interchangeable payload problem is we have a very clear, distinct line. It's an interface, an API, if you want. It's a modular decision that allows any of our large portable nodes to go on any of our vehicles. And I'm showing here the two most popular ones. One is our large drone, and the other one is a rover, but the same payload goes on our helikite, which is a combination between a kite and a balloon. It goes, we have a vehicle, a car, a full-size car that we go around with. We have a cart that we do experiments with in all our portable nodes. Work on any of these vehicles interchangeably because we defined a very clear mechanical, electrical, and control interface between them, right? So if you see here, it's a sample of our vehicles. These are our portable nodes mounted on these various vehicles at different times. Okay. The portable nodes, especially the large portable nodes, have also a modular design. You see, they are organized in plates, which are really easy to interchange. So there is a single nut that it's a butterfly nut here. That is so what a wing nut is called in English. Sorry. That can be easily unscrewed, and then any of these plates can be changed. So we can use the same computer with different radios, or we can use the same radio with different contents, or we can exchange the antennas, right? If you want to have directional antennas or change the polarity of the antenna, is really easy. At the base, there is a power plate that provides all the voltages filtered to the entire rest of the node, right? We have 19 volts, 19, 12, and 5 volts available throughout the node. The computer, it's a pretty powerful one. It's a laptop class computer. It's a Intel i7 with 64 gigs of RAM with a 2 terabyte SSD. So it's powerful, but that's what is needed to drive these radios. It's also heavy. That's why our big drones are big, is to be able to lift this. So let me see if there are any questions on the portable node, and I don't see any questions. So then I will go ahead and start to describe our thought process on choosing a drone solution to satisfy our requirements, right? So here are the requirements. And the first thing that we were advised to do, and we are still asked all the time, why on earth did you build your own drones and didn't use a DJI drone? There are so many other research groups that just use the Matrix 600 to do things similar to what we're doing. And honestly, in terms of hardware, the Matrix 600 is not quite exactly what we need, but it's close. So the payload our payload requirement is 3 to 10 kilograms. The Matrix 600 flies up to 6 kilograms. For most of our needs, that would be okay. Not great, but okay. Endurance is not quite there. It's a 35 minutes without payload, 60 minutes with 6 kilograms, probably on the order of 20, 25 minutes. We could have lived with that. It's certainly a small UAS. It's easy to interchange everything. It's very reliable. Now, when it comes to open design, that's not it. And community hardware, that's not it either. However, our main pain point for this solution is on the right. The software is all closed. The autopilot is closed. The communication solution is closed. The control software is closed. They give us an API, but we can only do what they let us to do. And if tomorrow they change their mind on what we can do, then we can be out of business. And so a lot of red on the right on the software side. Now, other people suggested that what we could do is to lobotomize the DJI and pull out the autopilot it comes with and put an open source autopilot. And that greenifies all the software, right? There's still some problems here. Now, the thing is, this is not an easy integration. And we lose a lot of the reliability that was built in the drone because the autopilot is probably not going to interface with a lot of the sensors that the DJI has on it. So it's an difficult marriage, let's put it like that, right? To have open autopilot software with the DJI hardware. So our first iteration was, how about if we get off-the-shelf frame with an open source autopilot? I think that's gonna work, and this is what we tried first. And so what we tried first is we got octocopter. It's a pretty big frame, the Tarot T18. It's a reputable brand. And we said, all right, let's build the first prototype. And the first thing we did is we tried to put the motors on, and we discovered that the motors don't fit the motor mounts. So no problem. We went to our CNC machine, cut new motor mounts, replaced the motor mounts. And then we said, okay, now let's put a portable node under it. And we discovered that the bottom plate is unsuitable to put a portable node. So we had to go and cut a new bottom plate. And then we said, let's put the batteries. And the batteries were too big and didn't fit. So we had to go change the top plate. So now you can take our big batteries. And now everything was kind of heavy for the frame. So the legs gave away. So we went and exchanged the legs. And then we looked at the drone and it's like, what did we actually use out of that original frame? And it turns out that the only thing that was still active was the arms, the tubes. So we started asking, like, is that even worth paying any money for this frame? And to answer our question, Thales discontinued the frame. It's like, all right, so that's not a question anymore. So what happened is it just didn't work out for us. So what we did is we simply designed from scratch in SolidWorks, screw by screw, over 1,000 parts, hexcopter, a large hexcopter that has a max takeoff weight of 30 kilograms, has over 75 kilograms of thrust. So that's what determines the max takeoff weight. Of course, since we're flying under Part 107, we keep it under 25 kilograms. But the propulsion system can handle more of that. And has a no payload flight time or 47 minutes. And our standard portable node has over 35 minutes, right? So in that respect, it outperforms the DJI Matrix 600. And the payload standard battery is up to 16 kilograms, 11 to standard Part 107. And it has been designed with a lot of redundancy in mind with the dual GPS with RTK, triple redundant heated, and so on. Right? So we have we build this from scratch, and therefore it fits well with our batteries and everything. Right? So these are pictures on how we implemented it. Was we essentially bought carbon tubes and carbon plates, and out of the SolidWorks design, we went and cut the parts. Right? This is one of the two main plates. There are two of these that create a sandwich that hides all the electronics and the controls. And these are the parts being cleaned up. We also designed a two PCB solution. The top one is the control side. The bottom one is the power side, is power distribution and control. Right? The connectors you see here each go to a motor and ESC motor that are mounted at the tip of the arms. And this is how it's in flight. And so this is we have currently 3 of these working. The 4th one is being assembled, and we're working at variants. In particular, we're looking at a heavy lift. For that, we will need an FAA exemption, but our administrator that's taking care of that said that should not be a problem for us, right? So this is our hardware solution for the drone question, so to speak. This is how we test it. We have a test stand with blocks, and the test stand has, out of the 6 degrees of freedom that the drone normally has, this preserves 4. So it's all rotation, right? You can have your pitch and roll, and it also goes up and down. It's just X and Y that's restricted. And the reason we do that is because every time we mess up with the drone, we open it up, we change the propeller, we change the motor, we build a new drone, we want to test it here first, right? To make sure if something is wrong. And at some point, something was wrong, right? So our second drone we built, one of the motors wasn't working, and we were so happy we were on that we discovered that on the test stand rather than in flight. Let me see if there are any questions about our big drones. And the answer is no. There are no questions. So then after figuring out the big drone, we repeated the whole process, now with a lot more experience, with what we called our small AERPAW multicopters. And those are not that small. There is still a good, I think, I don't know, 60 centimeters or so, tip to tip, 60, 65 centimeters, I believe, tip to tip, and 4x18 propellers. This could lift one of our big nodes, but usually we don't. Usually we go with small portable nodes, much smaller portable nodes. This has, interestingly, even better flight endurance than our large drone. So we have a 60-minute with standard batteries, but we clocked it for 1 hour and 22 minutes with a bigger battery, with a 30 amp hour lithium, with a payload, right? With the standard payload, which is a single board computer. It's a Latte Panda computer with an LTE modem and another radio. Uses the same autopilot and the same controller as our large multicopters. Okay, and likewise, we have a custom PCB. The PCB not only keeps everything nice, light, and tight, but also increases reliability of the entire system by removing different points of failure. And this is our fleet of small drones. We have 5 working at this point. We're building 2 more, and I think then we'll have enough to last us a while for what we need. right? So typically for software-defined radios, we fly the large multicopters, and for COTS radios, we fly our small multicopters. This is the size comparison of the two, right? It's hard to tell them unless they are side by side, but this is our large multicopter, this is our small multicopter, and this is in comparison with something that would probably is familiar to you. It's a DJI Phantom. This is how they compare size-wise. We also have a working rover that it has 120 minutes endurance, so it's 2 hours can drive. Of course, if it sits, it can sit forever, or not really forever, but for days. One of these large batteries can power a portable node for 2-3 days, depending on what it does. And this works great as long as the ground is relatively level. If it's grass or road or everything is okay. As soon as we try to take it on a plowed field, this shakes quite badly because it has no suspension. So for this reason, our second rover that we're working now at, it's considerably bigger, and it's really designed to work on the fields. And we'll continue to keep this one for smooth surfaces, but our second one is going to be the one that can cross the field at speed in any direction. Okay. And this is in its natural element. We are doing some tests to see how it comes back to where it goes. So let me see if there are any questions regarding our hardware. And I don't see any. So we're going to jump in our software. And what I want to explain is our main problem is, remember, we said programmable radios and programmable vehicles. And the question is, how do you program a vehicle? And the key ingredient here is the you. Who is the you? The answer is, this platform that we're building is open for experimenters. So experimenters can come to our platform, not physically, virtually, right? So they log in our platform and then can tell our drones what to do, right? So there's going to be experimental code running on that portable node that tells the drone what to do. How can an experimenter can do this? And we look at all our other test beds, and all the other test beds give the experimenters live access to the test bed. That means an experimenter gets scheduled for Monday morning between 9 and 11 o'clock, and you can log in on these 3 nodes, and you can write your code and test your code, and everything is fine. We cannot do that. We cannot have drones in the air and the experimenters write their code and test it. That's completely unacceptable. Not even if the drone is on the ground, it's still unacceptable, because it costs money and time for us, the operators, to go to the field for just the experimenter to develop their code. So for this reason, we had to build a whole other test bed, which is a digital twin of our real test bed, right? So we have all hardware test bed outside with hardware drones and hardware computers and the hardware radios, and we have a second test bed in a cloud that is exclusively used for our experimenters to set up their experiments. So in this second digital twin test bed, and to be clear, and then we move experiments between the 2 test beds. So our experimenters, instead of coming and getting live access to our hardware, the experimenters come in and get live access to a digital replica of our software and hardware, and they develop in there until they're happy, and then they press a button, and then we move their experiment from the development mode to the testbed mode, and we move. What we're actually moving is this They are called EVMs, which is experimental virtual machine. They are not EVMs. They are really containers. So we're moving containers between the digital twin, which is the development mode, and the real test bed. And then we run their code there. But they develop and they test their software in this digital twin. Okay. So that's what led to all this craziness. And now let us tell you how we did it. And in the digital twin, all the software that runs in the digital twin also runs in the real test bed, except for two things. One of them is we have no drones. We have a drone emulator, and I'm going to talk about it a bit more. And the second one is we have no air for the radios, so we had to also emulate the channel, the wireless channels. And we currently have, after quite a bit of development, we have both of these working, including the moving in and out of the test bed, right? So this is what I will focus on, right? So today there is an entirely different story on how did we emulate the wireless transition, and that's I think a very interesting story as well. I'm in charge of that as well. But today we're gonna focus on this part, on hey, what's the software solution you have, and how exactly do you program drones in the digital twin and you move them out to the field, the same software out to the field. And here is a zoom in that particular part. And there is going to be another zoom in on the top, but let me explain how this works. So on the test bed, you have a vehicle, which is down here at the bottom, which is a frame, right? It's just motors, and you have PWM controls, the speed of the motors. And then you have an autopilot, right? For us is a orange cube, pixel compliant. And then we have the software that runs on the computer on the portable node, right? So I'm just showing here the Intel NUC, but this is part of the portable node that then talks via a USB cable to the autopilot, and it tells the autopilot what to do, and the autopilot commands the drone to make it happen, right? So this is what happens, and then there is vehicle software that allows this to happen. In the digital twin, we have everything the same up to the frame. Essentially, we still have the same control software for the vehicle, including the mapping filter. I'm going to talk about the mapping filter. I'm going to talk about each of these blocks. And then we have the autopilot firmware. So exactly the same code that runs on our autopilot hardware runs in an autopilot emulator. Right? So this is identical one-to-one. We make sure it has the same version of the firmware so we don't have surprises. And finally, instead of the real frame, we have a vehicle physics simulator that responds to commands from the autopilot, and it feeds the autopilot with simulated sensors so the autopilot can do its job. And in case you wonder, how do these two compare to each other? I would say outstandingly. You put the graphs, either location or altitude or speed, or any two graphs you want to put one over the other, you can't see the graph that's at the bottom. It's that good. I'm sure eventually if you push it too hard, there's gonna start to be a divergence. But for what we do, up to 20 meters per second, which is, I don't know, 50 something miles per hour, these two behave identically. So we're good to that. Let me see if there are any questions. No questions. So I'm gonna go ahead. And the first thing I said I'm gonna explain is what's the deal with the Mapping filter. And let me explain what that is and what its purpose in life is. Our experimenters have access, not only access, have root access. They can change anything they want in this container. This is called the experimental virtual machine experimental container. All the software they write is here, and we encourage them to write it on top of this software stack, but we do not force them to do that. They can do whatever they want in terms of programming the drone, as long as they speak standard Mavlink here. Now, Mavlink, if you're not familiar with it, it's a micro air vehicle link. It's a pretty common standard for communicating with vehicles. It has usually two different sets of links. One of them is commands going towards the autopilot, and then there is status, right? So you know where the drone is, what it's doing, what is the current speed, what's the level of the battery, and other things, right? And Mavlink is super powerful. It's in fact so powerful that it's scary, meaning it has commands that allows an experimenter, for example, to stop all the motors in midair, right? They can take a drone 100 meters up, and then they can command all motors off. And it's gonna do it, and it's gonna crash mightily. So for that reason, we have a piece of software, piece of custom software that we wrote called the Mavlink filter that is is intermediating every command that is being sent to the autopilot, and the judges it, and it says, you wanna go to a certain point? Let me see, is that point valid? Is it within the geofence? Is it within a no-go zone? Is the trajectory going through a no-go zone? If any of this happen, it's gonna say no. For the drones, it also watches the altitude. We have a minimum altitude, we have a maximum altitude. We allow changes of the yaw angle. We can allow takeoff and allow limited mode changes, in particular to guide, and we allow the drone to land. We do check where it lands. It needs to land within 10 meters from where it took off. As long as that's satisfied, we're good to let it land. Okay, so for every movement, we watch everything going through, right? So this is currently what we do, and as long as these conditions are satisfied, we pass the command to the autopilot. If we see anything funky, we cut the link and we say, yeah, this experiment is aborted, and we stop the experiment. Okay. All right. Let me see if there are any questions. No questions. So I'm gonna go. I'm gonna go now to on top of that, on how exactly we allow our experimenters to program the drone. So I want to point out that the Mavlink filter lives in a separate container called the control container, control VM, to which our experimenters do not have access, right? So there is no way for them to bypass the Mavlink filter. That's part of our safety policy. Now, the way you can program our vehicle varies a lot with what you need to do and how comfortable are you programming. And we already provide a series of sample applications that you can just use. And for example, pre-planned trajectory is our most popular one, and you can just edit the mission plan file using a GUI, upload it, and say, yeah, I want the vehicle to do this, right? And that's already a lot of freedom, given the fact that you get to choose which way the drone is oriented, how long to stay at which waypoint, what to do in transit, what to do at waypoint, what the speed is, right? So you have a lot of choices right there. But if you want more than this, you can change, you can modify the software that we give you. And if you don't want a pre-planned trajectory, you want something else, you can write a different application based on our library. That we came up with a library I'm going to talk about you in a second. And if you don't want that, you can build something on DroneKit or PyMatlink or really anything you want. As I said, our users have full freedom what they want to do in here. As long as they send valid Matlink commands, we're happy to execute the commands, right? And we feed all the status is fed back here. Okay. So the way AERPAW works, right? This is a library that we developed from scratch, right? I mentioned John Kessler. It's his baby, one of his babies, to be exact. He did a wonderful job of defining a finite state machine. And this is, for example, the finite state machine for the pre-planned trajectory, where essentially what it does, it takes off at the altitude that the experimenter specifies. Then it looks into the plan file and it retrieves the next waypoint, and it starts going and doing things, whatever they want, while in transit, and then getting to the waypoint, doing things, whatever the experimenter wants at the waypoint, and it goes to the next one, until at the end, it RTLs, right? It returns to launch. And that's something that AERPAW makes it really easy, I think, in my opinion, because you have each state, right? As long as you can plan your execution as being a series of states, and each state can lead into another or in potentially different ones, right? So you see the next waypoint, if it exists, it goes in transit. If it doesn't exist, it goes to the RTL state. Okay. And AERPAW also has support for coordinating multiple vehicle movement, right? You can have swarming, in which multiple vehicles synchronize their moves. So it offers synchronization points, it offers exchange of data, primitives for exchanging data between vehicles, right? So one can decide something and communicate to all the others, and they all execute. It provides support for autonomous drone movement, safe autonomous drone movement, I should say. And it handles all vehicles. You can actually run the same script on a rover. Our same pre-planned trajectory runs both on the rover and on the drones. Of course, the takeoff commands and land are ignored on the rover. It just cannot do it. Here on the right, I have a sample of some of the things we're doing, right? If you recall, we are a wireless test bed, so we're measuring signal strength. So you can see a heat map, a 3D heat map of our field. We have here a fixed node, and we had our drone do these zigzags, and while it was going in these zigzags, it measures signal strength at different altitudes to see the effect of movement of the drone as it tilts and pitches and rolls, as well as the antenna patterns. Okay. And these are the pre-planned our sample applications, and by far our most popular application is a pre-planned trajectory, is the workhorse. This is whenever you want to go there, do something, go there, do something. This is the way to do it, is the easiest way. Allows the users to have GUI definitions. Essentially, they use QGram control, which is point and click for plan files, and allows the users to pause at waypoints for however long they want, change speed from waypoint to waypoint, or overall change in the yaw, or keep the yaw fixed throughout the flight. And it has software hooks for things to do while in transit, if you want to do measurements, or at waypoints, or both. Okay. We also have also pretty popular GPS logger, which doesn't control the vehicle. So this is what we do when we have a cart that a student pushes, or we have a vehicle that somebody else drives, or we have our helikite that the helikite goes wherever the wind blows it. Then the GPS logger it logs all the tilt and yaw and roll and the azimuth and the position. We also have a sample for multiple vehicle control, which is really a choreographed dance between a tracer and the orbiter, right? So there is the picture from one of the flights in which the tracer goes places and the orbiter goes and orbits around it. If you want to do measurements around mobile nodes, this is the way to do it. And finally, we have an example, a sample for autonomous vehicle movement, which we're using for our Find the Rover challenge, AERPAW Find the Rover challenge, in which we have a rover that we hide in the field, and our competitors, we have a challenge ongoing, and the competitors try to use a drone to find the rover either as fast or as accurate as possible, right? So that's the basis that they built on this sample application. And finally, if you had anything to do with autonomous drones, you're probably familiar with Q-ground control. And this is what we offer both to our experimenters as well as for us. We use it in the field. Our safety pilots use it, our operators use it. And it's a great control station, has support for multiple vehicles for MAVLink. It has versions that run on tablets and phones and controllers. And I see Kamesh is blinking at me, so I think I will finish. This is the last slide, Kamesh. I wanted to point out that a lot of what we're doing is to increase the safety of our operations. And it starts from the hardware, in which we have more propellers than we need and more thrust to weight ratio than we really need. We have multiple sensors for everything. We have separate control links. We have RC controlling and cellular different frequencies. And this is on purpose because it's quite possible for our experimenters to jam one of the links. We think it's impossible to jam both of them. We have different power sources. We have different antennas diversity. Now we fly with all arm checks or fail safes. And a lot of software was written just for making sure that that everything is safe, starting with the emulator itself and with the MAVLink filter that restricts of what can happen. We recently install an ADS-B alert system that is watching for incoming, because it happened more than once to have helicopters that are flying way too low over our field, and we want to have a heads up when that happens. And we fly under Part 107 rules, and we have excellent trained safety pilots. And as promised, that was the last slide. So now I think it's a good time for questions. I do have the chat open, so if you do have any questions, do not hesitate to ask.
Yep. Thank you, Professor Sichitiu, for a wonderful presentation. This is pretty unique project or a platform, and I believe there is some initial those who are attending now, if they're the first time they're listening to this platform, it takes a bit of time to understand and then engage in this activity. But I think it's a great opportunity, especially for the students, to look at this platform and see what it offers, as much as you learned today in this presentation. And please follow up if you are interested in doing any projects on this platform. I think this is definitely a great opportunity for students to engage in the research.
It's not only students, it's also researchers, and not only at universities, but also in the industry. We welcome all in all. Everybody is welcome to our platform, and this is as I said at the beginning, it was the intention of NSF to be a place where both industry and universities come together and bridge the value of death. And I do believe you are right in that it's unique, but I think it's only unique because nobody else tried to offer this level of programmability to external users. Because if this would have been us, a lot of what we do is non-native, right? Because we trust us completely, but we do not trust the experimenters, and we build things to be able to handle the experimental code in a safe manner.
Yeah. So, Mihail, there is one question, it was actually sent to me, but I will read it for you. I'm not sure, this question is, somebody is asking, I'm not sure if I understand correctly the difference between high-end simulators, for example, some simulators allow you to even use the simulated drones using physical controllers. So I think the question is, how it is different from someone doing on their own, on their using, for example, the other simulators that are currently available. I mean, obviously, there's a huge difference, and please see whether you can explain them.
Yeah, so I think the key difference is that we use the exact same firmware and soft completely to the last line for the autopilot in both our emulation environment as well as in the testbed environment. And what this allows us to do is to have unchanged applications behave exactly the same in the real testbed and in emulation. So it adds a layer of safety that is not available if you simulate the entire drone, right? So if your entire drone is simulated and you do something that's close, but sometimes not close enough, then you end up with discrepancies and potentially different behavior if your software then has decision points that are time dependent or distance dependent. So I think that is the key. We have a simulator at some point, right? So the frame and the frame behavior is different, but as long as the frames are capable of implementing the commands that the autopilot gives, then the two behave identically. Right? So if we would have a lame frame that could not keep up with the simulator, then that would be a problem. But
Yeah.
we don't have that problem.
Right.
As a matter of fact, our frames go at 2G up. 2G over the 1G from the Earth. So when we max up on the throttle, our accelerometer shows 3G on the up. So it's a very capable frame. That's what I want to point out. So there is not a question that our frame cannot keep up with the simulator.
Yeah. So then I think one more thing, probably, would you please share few words on the ongoing student challenge or competition that is currently in process?
Absolutely, I would love to. So this is a competition that we organized here, and this is a key to it. We have 6 teams currently working and developing their software, and I am home. I'm not at the field, right? Trying to support them because they can do all their job in the system, and when they are done, we'll take the software and test it at the field, right? So first we'll test it in emulation ourselves, but then we'll take it at the field. Now, what this challenge is about is trying to find a transmitter, and we have a relatively narrow band transmitter on a rover, which we place in one of our fields. This is the rover. And we have a node like that has a custom waveform that gets transmitted at one of our fields. So let me see if I have a picture with our field here, right? So we go and hide that over here, and then the participants, the competitors, if you want, they have their software controls the drone that also has a radio receiver, exclusively receiver. They do not control what our rover does, either radio-wise or movement-wise. So the competitors can control what the drone does, both movement and radio, and their job is based on the signal strength that's coming from that's being received at the drone, is to find their best estimate for the rover. In particular, we have two times. We have a fast estimate, which is 3 minutes. So give us your best guess in 3 minutes. And then we have a second one after 10 minutes. You can have the drone for in 10 minutes. In 10 minutes, you can scan a lot of our field at 10 meters per second. And then they can give us all their best estimate. And at the end, we'll award two different awards, two different prizes. One is for the best fast estimate, and then best accurate estimate, right? The slow estimate. Possibly to the same team, right? If they end up winning both, we don't mind. But this is what the challenge is about.
There's one more question from it came actually through individual messages to me and Katie. Is there any version that can fly and be controlled in the night?
In the night, we do have our drones have what it takes to fly through the night. Namely, in here, actually, I think I have a bigger picture here. We have an FAA beacon, which is FAA approved, and it has the right level and the light blinking and the right everything. We actually, in our newest versions, we have two, one on each arm. We have two beacons. So we are good to fly in the night. It's just that we didn't find a good reason to do it. The only thing that happens quite regularly is in the evening, we didn't quite finish our experiments. So in the twilight, in the civil twilight, we just, wrap up our experiments. But so far, we never flew intentionally to start at night. But yeah, we really don't need a different drone. We just need we need permission from FAA to do it, and a good reason. I think these are the two things.
So that question was from Madan Pandey. Yeah, now I don't see any more questions, so we'll try to wrap it up. First of all, thank you, Mihail, for the wonderful presentation, and I'm sure. So I see lots of students as well as professionals, and some of my colleagues are also here in the audience. It's well attended, and I request all the participants to follow up on the activities by going through the website of AERPAW. It is very easy to find. Then look at the user manuals, read the user manuals, and follow up with Professor Mihail Sichitiu for any further clarifications. And please attend the next meeting. Typically we have on every first Monday of every month. And finally, please look at the last slide that we are showing on the screen to reach out to become a member. If you are not already a member, please join the society, Vehicular Technology Society. We have a lot of activities like targeted for students as well as professionals. Once again, thank you, Mihail, for the presentation.
Thank you, Kamesh. It was wonderful to allow me to speak about what I love to do and what I'm passionate about. And anybody that has any additional questions, please do not hesitate to ask.
Okay. Wonderful. Thank you.